morning to all of you. So you are warmly welcome to 29th Research Lunch. So today's discussion focuses on a highly inspiring and intellectually important theme: how to conduct fundamental research, insight from robotics and AI. So let me introduce today's resource person, Dr. Chapa Siritunga. Dr. Chapa Siritunga is a Marie Curie Fellow at University of Cambridge, working on human-centered robotics and embodied intelligent research. She completed her PhD at University of Moratuwa and will soon join University of Bristol as an assistant professor. Her research focuses on human-robot interaction, then embodied AI and robotics. So as a University of Moratuwa product, so we are proudly hear your story. Dr. Chapa, so our doors are open to you.
Thank you so much, Dr. Naini. Once again, thank you so much for inviting me here. I'm so glad to be here and talk to you because I did my PhD here, both my bachelor's and PhD. So it's so nice to be back and speak to you all. So I will focus on a general theme, how to conduct fundamental research. And my research is from robotics, human-robot interaction. And I use AI for design and computation of algorithms as well. So I will draw insights from my own experience and also my peers. So I will share my experience on fundamental research that I conducted in Cambridge. So before I move on to my work, I'll introduce my journey. So I started my higher studies at University of Moratuwa. I did my bachelor's and PhD at the electrical engineering department. And I finished my PhD in 2020. And then I served as a lecturer for a brief time during the pandemic. And then I joined University of Moratuwa as a postdoc researcher. And while I was doing my research there, I got a fellowship to conduct research for additional 3 years. So I stayed there for a little longer than expected, and now I'm almost done. So, and you might know already, Cambridge is an independent university, and it also has colleges. So these are independent bodies that support undergrad education, also postgrad as well, as an additional institute. So they have further supportive system around students. So I'm also affiliated with a college, and I would be happy to talk about these experiences as an interactive part after this presentation. And now that I have finished my fellowship, I'm joining University of Bristol as an assistant professor this summer, and I will be starting my research group in assistive robotics. So that was my journey, and in the meantime, I also visited a couple institutes such as EPFL, University of Tokyo and Oxford for brief amount of time to conduct research in these institutes as well. So yeah, that was my journey within the last couple of years, 6 to 7 years. And these are some photos during my PhD experience in Moratuwa. So I was working on human-robot interaction and service robotics, how to design robots that can be around you and then help you with certain tasks without bothering you or invading your personal space. So, yeah. Moving on to today's topic, I would like to talk a bit about fundamental research and how to do it, and then I will show you some examples from my lab, my own research, and also my colleagues. So if you have questions, feel free to stop me anytime. If you want more explanations, I'll be happy to discuss it more. So I would like this session to be interactive rather than me delivering the whole concept. In Moratuwa, I was conducting very practical research, like research that can be applied immediately, that you can see an impact. But what I'm talking today will be different from this. So I would talk about the top-down approach. You start with a highly conceptual idea, and then you think about how to implement it. But when you think about the resources you have and think about the limitations first, you go from a bottom-up approach. You start with whatever resources you have, and then think about what you can do later. But that immensely limit what you do. So that's exactly why I decided to talk about the fundamental research specifically. So fundamental research can expand our knowledge and understand fundamental principles like, if I talk about a very broad topic, why humans exist. So these philosophical questions can easily lead to fundamental questions. And then they are very much curiosity driven, and they're very open, sometimes too open to find an experiment to simply find some results and analyze it and then find the answer. So these can easily be infinite. So you have to be careful when you do fundamental research, but it's very important as a researcher, when you grow up to be independent, you have to think about the fundamental way of thinking about your field, because once you graduate, you become a leader and then you lead your field. So you should have this big vision to have a plan for your lab, for your team, and then lead them. So there are so many other reasons why we do fundamental research, but these are some basic ones. And let me show you some examples. When we talk about fundamental research, many think that it's limiting the applications, the immediate impact is limited. It can be true, but it's not always true. And these are some examples. So, for example, when they found human genome, I think around 23 or something, they didn't see an immediate, they had an immediate impact, and it could generate personalized medicine, personalized treatment plans, and then targeted therapies. So it could immensely make the healing process faster. But there were some findings like mRNA technology and general theory of relativity, which took a while, several decades, to transform into applied research. But they are extremely important nowadays, such as GPS technology. Now all of us use it. And also we used a lot of vaccines during the pandemic, and the technology behind that was invented a couple decades ago, but it took time to prove that it's important. So there's this impact problem in fundamental research. It's not really a problem, but you have to be prepared for that. And when you do fundamental research, there are certain aspects that you have to think of, you have to bear in mind. Like this research can be a little longer, like when you engage in your field for a while, you know the nooks and crannies, and then you know this fundamental question is unanswered in my field for this many decades, and there could be reasons, and you are the best person to know that. So you know how it can fundamentally change the field. So your finding is going to fundamentally change the way all other researchers look at that. So you have to create a nice story, no matter how simple your finding is. If that story can change the way we look at something. I'll give you some examples later. So you have to pitch it nicely so the readers know what kind of impact this finding can bring us. And then if we talk about the papers, usually we publish fundamental research in Nature, Science. They love good pictures, good figures, and nice multimedia, because that's the way you can convince someone to adopt your story and apply it in their field. So you have to show it nicely. And as I told you, this can take long periods. You have to be in the field for a while to understand these concepts and deliver a good finding. And having a good team is extremely important. I will show you how this happened in my team and how it can affect you as well, because someone with a good vision and then your supervisor can lead you, and then there should be someone to build something, and there should be someone to program something, and all together it should actually happen. So having a good team is extremely important, especially regarding the timeline of your projects, because some projects can be dragged along years and then there's no output. So usually my approach is to do experiments as fast as I can. So I think of the easiest way to do an experiment to answer that question. So that saves a lot of time. And this is an idea to think about when you plan for a big experiment. And this is also important for paper writing in general. There can be a finite way of doing it or infinite way. Let me explain it a bit more. You can take years, like 3-4 years, and then conduct experiments, try different designs, try prototypes. And for this whole period, you don't publish, you don't reveal much about your research. And then in the end, you collect all your findings and publish a big paper, which has a big impact. Usually these can change the field very much. Like when they introduced 3D printing, for example, everyone adopted it and it changed the industry as well. So many companies merged from 3D printing, and it basically affected pretty much every field. And then you can also take small steps. You can either do an experiment or you can focus on simulations. And then you can publish along the way. You do something small, but it's adequate to publish something. And then you can keep doing this. And then you can have a broader perspective in mind, and you can publish certain aspects of it from time to time as many papers. And then in the end, you know how to combine all of these together, and then you can publish a big paper. So these are different ways of doing it. It all depends on your vision. But most of the time when you start as a student, you don't have a big vision. It takes some time to have this vision, and then you go for this no experiment approach, or experiment plus many papers, but you don't know how to launch this as a big project in the end. So it's if you're in the middle of your research, it's nice to think about it now. Then you will know how to direct your research for a big outcome. And there are various ways to challenge this approach. Usually, globally, this applies how you can be challenged and how your skills can drive the challenges and move forward. So this is the usual way of moving forward. You will have certain skills, you will get challenges over time, and you keep growing. You get additional skills, you have certain amount of creativity, and then you have your knowledge. But in the academic journey, there are so many barriers like rejections. So during this journey, when you have your first rejection, you usually retract for a while, and then it takes a while to regenerate and move forward. So it's not ideally upwards, but you will have ups and downs. But the important point is keep going, and this arrow should point upwards. And you will get journal rejections, which can be really harsh. And if you can go past this, and you will reach a certain level up to like science or nature level rejections. There's a special thing about these paper rejections at Science and Nature. Usually editors are knowledgeable in the field, and if they think it's not a good match for the journal, they will just reject it. That means they don't send it to reviewers. They just decide that this is not going to work, and then they return it to you. So if you go past that, you have already achieved something. So reviewers can, of course, reject, but it's less likely compared to journal rejections. So if you can go past the editor, that's already a big achievement. And then, of course, you can target for big prizes in the field, like Nobel field prizes and so on. So those who try going beyond science and nature level can achieve a lot. So it's important to have this vision to pass this level in your field. We all talk about paper writing now, and the number of papers that are being published around the world exceeds millions now, especially with AI and so on. So it's important to understand why we do this, because if you have something important, you have to publish and show it to the audience. You can, of course, do it for your academic career, for your CV, to find your next job. But if you are in research, you will have a bigger goal, like establishing your own team, own group of research, and then getting more funding, attract new investors, and so on. So these numbers can show you some how these papers are worth. Like if you can go for like science, nature style, it can attract you a lot of investment, a lot of future opportunities. You can see how monetary value works here. And then, of course, to increase your research, increase your knowledge, you do research, and for communication and collaborations. I will talk about the importance of this point towards the end of the discussion, because communication, networking, and collaborations are a must if you want to thrive in your research field. And also you have to ground your research in this world. People have to recognize it and then support you in your research, collaborate with you, and go forward with you. And yeah, and this is a lot of work. And you can start research first and then do the paper writing. Usually my approach would be to have an idea. I start writing, and then while writing, I don't do experiments, but for certain fields, this might not apply, like chemistry. If you want to combine two chemicals, you can do it easily and see how it goes. And then you can think about writing. But for robotics, you usually, when you write, you can spot a lot of mistakes that you did while conceiving the idea and also designing, and then you can keep iterating without building a prototype. and then you can go for the completion. So most of the effort, as you can see, 50% of your effort will go to paper writing, and it can improve the experiments as well. And the rest will be divided among doing the research and submitting revisions. There can be several cycles, and then you should, of course, advertise your research. If people don't see your research, there's no point in doing it, because someone will publish it again in a couple of years. It happens a lot now because there are so many papers out there and we cannot read all of them. So it's important that you show it in a nice way. And these are the skill levels we recognize. So I adopted some of these ideas from my supervisor at Cambridge, Professor Fumi Aida. And we try to apply these skill levels for students. For example, undergrad students, when they do like summer projects, when you have a short break, like between semesters, when you have a couple months to do something, to build something, you can think about writing a conference paper, a short project. We call them low-hanging fruits, something you can do easily. And then you can submit it to a conference. And then as PhD students, you have to think about journal papers and keep the timeline as short as possible, because PhD is usually 3 to 4 years, and you have to finish your research that is adequate for a thesis. And then when you become a senior PhD student, like if you're in third year and you're writing your thesis, and if you're a postdoc, you can think about a couple journal papers a year. And then also as senior PhDs, postdocs, lecturers, you can think about science and nature level papers as well. I will explain how to approach this target, you can easily say science and nature, but you should have something to show, something people can adopt. So let's think about it later. And then you also need funding to keep your research going. You need investors to have trust in your research program. So you need to write grant proposals as well. So there are local funds as well, and there are also funds that are available worldwide. For PhD students, there are grants to travel to different institutes for a couple months, and then you are paid for your research, and all your expenses are covered. That's a small amount of money, and you can also think about big amount of money for fellowships. For example, I got the Marie Curie Fellowship to continue my postdoc research. So I initially got 1 year to be a postdoc, but that wasn't enough. So I wrote this fellowship application, and then I got additional funding for a couple more years. And that gave me loads of opportunities. So it's important that you think about getting funding as well. And thinking about paper writing again, you have different approaches. This is the general approach. You have a research idea. I'm talking about robotics here, but you can tailor it to your field. So you can build a prototype, and then you can run experiments, and then you write the first draft. And then you can keep iterating. If you find problems, you can keep changing your experiment, and then come to the writing part again. And then you do experiments again, and then you write again and again, and then finally you submit your paper. This has a problem. There are so many iterations, and this is not efficient if you have limited time. And this would be what I propose. When you have a research idea, you write it down, you write the first draft. You don't plot results, you don't analyze results because you don't have any results. but you can write the basic elements of a paper. For example, you can think about your problem, goal, hypothesis, and what would your results look like. So that can lead you to a nice experiment. So if you keep iterating this, you will find a nice experiment, and then you can do the experiment and then keep editing your paper. And if it involves hardware, you can, of course, do that as well. So to do this easily, we follow a 5-bullet approach. So in the past, when scientists were working alone, they had this approach as well, like how to find the science in your experiment. Louis Pasteur, for example, applied this research a lot. So he asks questions, he does research, and then he formulates hypotheses and then experiments that lead to publishable results. You can find out how he did it. He did so many interesting things, and his approach teaches you a lot of things. So when we have an idea, we write 5 bullets. Finding the goal is the most challenging part. So if you have a goal, if you know what you want to achieve, it leads you to a nicer place. Like knowing the KPIs, key performance indices, and then where you would apply, where your work will create impact. And then you define the problem. What are your obstacles to achieve this goal? You can, of course, approximate your results and then formulate the problem. That's not a problem. And you can also keep changing these later. Let's say you define these 5 bullets and then you conduct the experiment and it proves something else. You can, of course, come back and refine everything. But the important bit is having these in place. And then you have to have your own hypothesis, how you can overcome the obstacles with the resources you have. And usually you should combine mathematical models, theories that you have, equations, all comes into the hypothesis. For example, if you solve a manipulation problem in robotics, it's common to have this problem of manipulating objects, how we can do it, because we can manipulate very fine objects like threading a needle. But if you take a robot, it finds it really troublesome to do it. So what kind of models, what kind of theories you can use here, like computer vision, using control robotics algorithms, you can use AI, but you cannot say AI, it's too broad. You have to find the specific models, specific equations that can solve your problem. And then once you do the experiment, what type of proof will you have? What type of measurements will you take? Like what versus what will you plot? Let's think about the results. You know what kind of results you're going to collect, and then to show the answer for your question, what graph are you going to plot? That means X versus Y. You should define your X and Y. And then the conclusion, what are you going to learn or not learn? This method works for this method doesn't work for that. So if you have these bullets ready, it solves half of your problem. This is an example. This is one of our recent papers on science robotics. I was working on a lot of robotic hands, and so did some of my colleagues. And we were working on building robotic hands, fingers, and we did small experiments, published them. But in the end, that led to a design of a hand that anyone can edit anyone can modify it and create like weird shapes or human-shaped hands. So we wanted to publish this, and I will show you how it looks like later. And when we wanted to publish it, we just expanded the way we pitch our idea and decided to go for science, because we have loads of nice experiments, very simple, very low cost. And then we had a nice demonstration, and then it ticked a lot of things that are required for science and nature, but we didn't have a nice story. So the only thing was having that big picture, how to pitch it nicely. So before I go into details, I will show you how we did the 5 bullets. So when you pick a title, you can have a few iterations, but it should show your novelty. It doesn't have to show your results, but it should show your goals and novelty. So goal and problem. Goal and your contribution will be here. The rest can go into the abstract. You can give a small background and then your problem statement and your hypothesis, proof, and conclusion. So this has all 5 bullets here. So, goal was there, problem in the abstract, hypothesis, proof, and conclusion. So this is how you write a good abstract, good pitch. So usually thinking from a reviewer's perspective, when I look at papers, when I have to review papers, I look at the title, I look at the abstract, and then go through all the figures. I look at the novelty statement at the end of the introduction, conclusions, and if there are any multimedia that can simplify my computation, because I don't have to think about the paper. They show it nicely in a video. So having multimedia is also a plus. This is about that particular work. So we were thinking about a robotic hand. So this is what we had. This is OpenS CAD, if you're familiar with it. You can basically program without using SolidWorks or 3D modeling software. This is something like you program your requirement and then it generates a design. So you can design joints, different parts, and combine them together. And in the other video, you can see a real world setup that we printed in the lab. And then we tested it for different tasks, like picking, placing. This is all passive. It's tendon driven, if you're familiar with these terms. There are some springs attached to the fingers, and when you pull the strings, the fingers will bend. So that's the basic idea. And these strings have a constant force attached to it. So when it goes around an object, it just passively takes the shape of the object. So it can grab objects, manipulate objects without a lot of control. So this is simple, but we did, the design was interesting because you can edit it. You can have different test beds. For example, in the video, you can see a symmetric hand here. We have only our hand asymmetric, and we know only about that. And there were no animals with symmetric hands either. But we can be futuristic. We can think about a future application with maybe symmetric hands can do something better. And also looking at the past, you can see some primates over there. Some of them are not there anymore. Some are extinct. And they had really nice hands serving different purposes. For example, the the complete one over there is called II. It has a flexible middle finger just to forage in forests, look for animals in very confined spaces. So having this flexible finger basically helped it find its food. And then if we talk about gorillas, for example, they are like 98% closer to human in their biology. And if you look at their hands, they have short fingers, fat and chubby, because they mostly walk on ground. They walk on their palms, so it helps balance themselves. But if you look below, some monkeys who are always climbing from tree to tree, holding onto branches, they eventually got longer fingers because they have to be on top of a tree, not on ground. So different reasons and different parts of environment shape their behaviors, shape their physical features, and there are fossils supporting this statement, but some of the primates are no longer living on the planet. So we cannot understand how they manipulated food, how they use their limbs. So we thought our design can cater to that requirement, because if it's close enough to a gorilla design, we can also modify it to one of these extinct animals design, and then the hand can be a good representation for this extinct animal. So that way of thinking leads to a different perspective. So instead of having a traditional robot that can serve your needs, that can help you with daily tasks, this is a robotic design that can help paleontologists, for example, understand the missing bits of evolution. What we don't find as evidence, we can recreate it using, I mean, this is not completely like it's not alike, but it's a close enough mechanical design that can simulate certain requirements. So that was how we pitched the idea. We used a lot of biological indices, like how our hand works, how the bones are located, what kind of distances are there, how the digits are assembled on top of each other. And then we selected 3 designs, like inspired by human, and then one primate called II, and then another futuristic design with a symmetric hand. So this simple design led to this nice story about how to find missing bits in evolution and how to use robots to explore futuristic designs. So these are some results we found. It ticked some tests and it was performing very well, but the big story was this: how we can augment artificial requirements, artificial features into our designs, and also how to use our designs to explore the natural evolution, how to explore different environmental niches, because you can see here, for example, this skeleton, the fossils were not enough to complete the design. And for some designs, we don't even have fossils. So we can use these artificial designs to test the mechanics, and then think about how the skin was, and then scientists can forecast how their physical body looked like based on bones. So this can lead to a lot of other findings. So that's how we pitched when we created this hand for the first time. But if you look at the physical setup, it's quite simple. 3D printed. We only needed a 3D printer, filaments, and then some springs and pulleys to put the springs inside. And that's all. You just have to fix all these things together, and then you can use that in the experiment. What is important to think about here is the storyline, how we pitch that idea to cater to the past designs, looking at primates, simulating primates, and then we also look at human hand because that's the ground truth. That's what we have at the moment. And then futuristic designs that can solve certain problems in manipulation, for example. And then we had a very flexible design that is open source. Anyone can download and edit it. And it's low cost and it's trying to solve one of the biggest problems in robotics, that's the manipulation problem. And for optimization, we use AI. And this is important because we are moving into the physical AI era. So having physical designs that can perform nicely in the real world helps. And when we think about the nature and science level papers, having the concept diagram, we call it figure 1, is very important. This is our first diagram. The caption was longer, but I put a shorter one here. So it basically shows how this accommodates different customized designs and then leads to a physical design and then testing and proof. And then there's something we call figure 10. It doesn't have to be the 10th figure, but what we mean here is the results, how it looks like, what versus what will help you find the answers to your problem. So for example, in our case, we wanted the hand to perform very well, close enough to human hand or even more. In certain aspect, it performed better. In certain aspect, it performed worse. And then this is the result figure, and this is the highlight of your paper. So you can put your hypothesis as the control parameter or the x-axis, and then the proof for the hypothesis as the y-axis. And you can plot many ideally theoretical models on the same figure. And this should be something you have calculated already. Let me show you another example. This is from one of my colleagues who introduced this term, paleo-inspired robotics. That means robotics inspired by paleontology. The inspiration for this was evolution. When fish transformed into land animals, they had to walk to the land and they had to grow legs from their fins. But we don't have enough evidence to show that they walk to the land. There are certain fossils that can hint something, but we need more proof. So this is a guy who coined this term and also developed a robot that can show this transition, how a fish can walk. So the idea comes from biology, and then we build something from robotics, bio-inspired robotics, and then it can prove this concept called paleo-inspired robotics, and then it serves paleontology. And this circle goes on. This is how they did it. This is a very simple robot. You can see here. It's a 3 degrees of freedom robot that can perform the basic undulating movements of a fish. And it could replicate different gait patterns, walking, how different body sizes matter, and where should you place the fins so it can help walking rather than swimming. So this is how that simple robot proved a big concept. And extending from this I'm talking about 4 years of research here, leading to one science paper and one Nature paper. And this is their Nature paper, was an extension of the previous work. So when they did simulations on fish, from what they found out and how from the real fish videos and so on, they simulated fish, and then they found out that the fish that the simulation also shows something about the gait patterns when they reverse. A fish doesn't always have to go forward, it can also go backwards, but actually fish don't do that. But the simulation showed it's possible. And then they tested it in the real world. This is an actual fish, and they tried to make the fish spin backwards, and the measurements were compatible with the simulation. So that simulation led to a biological discovery. So it gave insight on how forward and backward motion can be possible in fish, and also the mechanics related to it. It will go online in a few weeks, I think. Resources for this work were very simple: simulations, MATLAB. You all have MATLAB, so you can do it. And then they analyzed some videos of real fish. They were speaking to a lot of biologists, so that's important, having right collaborations. As resources, they used only computer vision. But they benefited from having strong collaborations. They were collaborating with Professor Neil Shubin, one of the professors famous in paleontology, who found this fossil called Tiktaalik. You can look it up and find the story behind it. And that was a very important, groundbreaking discovery in paleontology. And also they benefited from initial results from simulations. And if you complain about hardware not having enough resources, this is another example. So the question, this is also from my lab, like 7-8 years ago. They were trying to understand how to model free paper falling. You all have seen leaves falling from trees. So if you try to model it, how would it be like? Or can you model it at all? So this is an attempt to do it. You cut a shape on paper, and then a robot picks it up. You don't need to do all these things. You can just cut a shape on a piece of paper and try to drop it without disturbances. So yeah, and then you analyze how the environment works and how these things fall based on different papers. And they found different profiles of falling down, and they tried different shapes of paper, and then they found 4 falling styles, and that was all for the experiment. So then started the analysis, and then from non-dimensional parameter space, which you cannot define, they led to behavioral groups that you can find in all types of falls. So it's pretty simple. You get a piece of paper, you drop it, and then you find something fascinating. So this is the incredible nature of this type of research. And if you think this is all research related, this is a recent example from Cambridge that these fundamental research can lead to industry as well. These professors found a spin-out for nanobot, which is now worth $1 billion because of the AI data centers and so on. And this is based on battery research. So you can look it up. I have put the QR code there. And the message here is that the impact can also go to the industry. to conclude what I've been talking here, fundamental research is close to you. It's closer than you think. You don't need massive equipment. Sometimes you need, but not necessary. It starts with curiosity, and it's about a groundbreaking story. And the discovery comes before the application. So you don't start with the application. So the problem is not in starting with the application. It starts with curiosity. And these are small ideas that leads to a big impact. So you have to think about the impact as well. And then having a good team helps these big ideas. And in Cambridge, you know how to do big research, and you can find out how to do it if I don't tell you. But what is special from where I did my research, that's Cambridge, is the push towards communication. Because as I told you before, we have colleges. They are small communities. You belong to a college, you go there, you speak to people. Usually I go there for lunch, and then there are some weird rules. You cannot sit where you want. You have to sit next to the next available person. So everyone starts filling the table from corner, and then it goes like that. So you don't choose who you sit next to, but you are supposed to talk to the person. So you speak to the persons next to you, and they're not from your field most of the time. And sometimes it's someone who won $1 billion for his or her company, or it could be someone who was the Nobel laureate from the last year from a certain field. So you have to talk and find out. You can share your research and share their research, and that's how collaborations begin usually. So I highly enjoy that environment there. And I think that's something we have to think about as well, because we are a social community in Sri Lanka. Everyone is friendly, so we can easily adopt things like this. Yeah, that's about fundamental research. I can answer if you have questions. And after that, I will show you a bit of my research, and then we will be done.
Okay, thank you very much for that insightful and inspiring discussion. So we'll move to the interactive questions and answer session. So dear audience, then I kindly invite you all to share your questions, comments, and reflections here.
I heard that always when we were thinking outside of this,
Usually you don't have all the resources, even should I tell this first? Yeah. Yeah. Okay.
But then
Things. That's it. Usually you're not from the lab that has the perfect equipment for your idea. So the best thing you can do is to invite someone who can collaborate with you, who has a background, who can back you up. So that's why I said it's important to have a nice team, so they can split the workload. So when we usually don't have the resources, we always encourage collaborations. Working with peers, it has to be from outside the other. It can be a different university, different department, different country. Always good not to have everything at one place. It also encourages discussions, because if you have an idea that is more relevant to psychology, biology, it's better to have someone from biology who can shape your idea. So usually it's not an individual game. It's much richer, much beneficial if you can have a support system. Did that answer the question?
Okay, so then this actually is not we are all facing these questions that I'm asking you. So then when academics and researchers, academics and researchers ask papers like the articles, so we are facing so many problems because then lack of resources, no databases, lack of funds, lack of resources. But then you are here discussing the strong research culture and these things. So with these things, then how can countries with limited resources still build strong research culture?
I think there are different ways to do it. One thing is communication, collaboration, as I mentioned earlier. If you don't have the resources and you still have a good idea, you can invite someone who can help you do the experiment for you, like a nice collaborative setup. And of course, this will have problems, how you travel, how you put everything together. So these should be sorted. But most of the time, having a good team, having the right team helps. So, and also there are so many things that you can do with limited resources. You can think about research questions like the polling paper example. You can have a box that restricts wind, and then you can make a simple setup that can drop a piece of paper without turbulences. And then you can record it through a web camera, and then you can analyze results. So for this, it will be really low cost, but it can answer something really impactful. So if you don't want to go for a big collaboration or something, you can also think about alternative ways to do it. Like, what fundamental questions are out there that I can do with these resources I have? Simulations are a great tool, I think. And also, nowadays, everyone uses AI, and it can shape your ideas very nicely. Especially if you don't have the knowledge in biology, for example, you can find out the basic bits using AI. It can summarize things for you. Yeah, but I highly encourage collaborations because that has helped me a lot. Usually, if you find right people, things are 100 times faster rather than doing it on your own. So you can decentralize your focus a bit and be open to collaborate more. And also networking. If you go to conferences, usually don't think about presenting your paper and coming back. You can organize a workshop. You can, of course, invite someone who can help you with that, and then you can keep discussing it further. You just need one moment to ignite the future discussions. So that helps. And there are so many online communities. We are also organizing a lot of online communities. So you're welcome to join us as well. Yeah, that's all what I can think of.
Okay, thank you. Then the audience, so then use this opportunity to ask questions. Any comments? Then the participants, so you can post, you can use online chat, or then you can unmute yourself and then ask questions.
So I think there is vision of vision of how we should conduct the experiments when we are like developing anything, and then do we have to compare with the existing world always? So is it adequate enough to conduct our own experiments when based on that validate our claims? So sometimes we feel that it's not adequate, that we have done enough validation with the existing models. So let's say for the parametric and show. So we can conduct experiments for applications of it. When there are other researchers that have been done in the same applications, we can't compare with all the applications out there. But what is the ideal part, which is enough or
There are multiple answers to your question. For our case, for example, there are so many robotic hands out there doing very incredible jobs. So the way we pitched it was different this time. So we didn't have to compare a lot, but we, of course, did compare. When you have to do a comparison, it's better to use a well-established experiment or previous work and then compare against it. That's always a good way to do it, good way to do incremental research. That's how reviewers believe in your project. If there's no comparison, then people can easily doubt, oh, this can be better than your proposed idea. So it's better to always have a benchmark that can evaluate your system rather than just saying this is much better. So it's always good to compare. And you can compare with already published papers or some of your previous work. If you publish something completely new and claim it's new, most of the time it's disadvantageous because there's a lack of trust. You're a new researcher, there are so many established people and they can easily doubt you. So it's better to give them proof rather than just saying something. And also finding a nice way to pitch it. If you have an experiment that has results similar to one of the previous setups, but if you can find a nice way to show it, or if it can serve a different purpose, you can find these loopholes and then pitch it differently. It's all about the story in the end, how you frame it. You can talk about humanoids, for example. So many humanoid robots are catching up. The market is huge now. Or you can think about biology, other fields that can benefit from your work. Did that answer you?
And Dr. Chapa, two researchers has posted some questions to chat line.
Okay, I'll have a look. Elaborate on most optimal methodologies of abstraction with the biomimicry. I don't think there's a particular answer for that because there are so many techniques to do that. Relating to my particular example, we use, for example, if you want to model the biology or anatomy of human hands, there's an index called Napier index. It explains how the distances in between your bones are located on your palm. So we use this type of indices, and I'm not sure what the most optimal methodology would be. Usually, as a roboticist, I would go for Bayesian optimization, that type of commonly used optimization algorithms to find out how we should transform the biological design to robotic design. And also there are different ways to think about different materials. So when we 3D print a robotic hand, for example, we think about what materials can go close to the human bone structure, things like that. But it only approximates the properties, but it doesn't replicate the whole thing. So I think AI can optimize so many things. You can try that as well. I think it's hard to optimize when we think about concepts like things from psychology, for example. Like I was studying pain for a while. how robots can understand physically grounded pain. If you have a wound, how a robot can synthesize it. Because we were working on medical robotic simulators and how doctors can use simulators to practice on them, because they can be 100 patients easily within 10 minutes. And if doctors have to wait to get that experience, it could be months and years. So for this type of cases, it's hard to quantify. We are trying to do that, quantifying certain immeasurable human aspects. So optimizing is not possible sometimes, but yeah, you can always think about computational techniques like Bayesian optimization. Okay.
Then next, what's mean by science and nature publications? The question.
It's about the high impact publishing rather than going for an average journal. If you have a groundbreaking results, for example, you found a cure for cancer, then you don't submit it to the next available journal. You can go for Nature, Science, because everyone reads them. So in the science community, people tend to read Science and Nature and trust Science and Nature more, and because of that, they create more impact. So they are very selective, and they think about who is claiming this. You have to have a good background to do it, and also you have to have the right result. So that's why it's different from Science and Nature. So these are just publishers. But the way of publishing is different.
Shall we continue?
Yeah, we can
Presentation
conclude.
now?
I have a couple slides if you want to see my particular research,
Yes,
but doesn't have to be. From this point onwards, it will be a little robotics research. So if you're wondering what I was doing, my research was mostly about understanding the human design using robotics. So I was looking at, for instance, how robots can generate facial expressions. And I was studying pain because pain is a high dimensional aspect. It has the social bit, how you express pain. It has physical bit, if you have a wound, how you react to it. If you have a tumor, how you react to it. These things are different. So it's multimodal, and your expressions are culturally shaped. It depends on gender as well. So it was a good point to start doing multimodal robotics research. And I was also looking at robotic necks, because South Asian community, for example, is communicating a lot with the neck, like head movements. So we were looking at if robots can do it, or whether it can deliver external information. And then I was looking at hands, fingers, legs. The reason why I did it, and if you look at your brain cortex, and if you scale the parts in cortex according to the computations which are scaled down to the organs it controls, this is how it looks like. It does a lot of computation about the lips, hands, and little computation goes to the rest of the body. Same for actions as well. So a lot of computation goes to control lips, because we talk a lot, and then hands, because we learn through our hands. If you look at infants, they touch everything, and then they gather everything about the world. And then I look at the face, how our face is delivering so much information, because we deliver up to about 25 bits per second. But if we look at all the robots we have at the moment, they go up to like 10 bits per second. It's very limited. So we are looking at how robots can deliver more information as a communication channel, and how to find like a common model that can help robots to deliver this information, and a lot of robotic necks as well. And this is a robot that can express pain. So as you can see, it can also show different genders, different faces like white, black, brown. So it's a good replica, good representation of many people around the world. And then we learn, and then different types of faces, like African faces here. And then we also have an abdomen setup to create physical pain, how it affects the face. So these are some of my research, and these are some things I built within the last 4 years or so. And you saw some of these, and all of these shaped what I showed you today. So that's how I started and ended up at the same time. So I was working on robotic hands, fingers, wearables, simulations, and also human-robot collaboration. So there's a lot of hardware involved. And there are some resources for you, further reading materials. And if you want to find more about my research, this is the link to my website. You can also connect with me. All the details are there as well. And that's all.
Okay, thank you. So as we come to the end of today's research lunch session, I would like to express our sincere gratitude to our speaker, Dr. Chapa, for sharing a valuable experience, insight, and inspiring academic journey with us. So I believe this session has encouraged many of us to think more deeply about our research, collaboration especially, and the possibilities that emerge when we pursue questions that truly. So I would like to thanks again to you and all participants and academics, researchers, and students who joined today's session and contribute to this meaningful discussion. So we wish you all the very best for your future endeavors, Dr. Chapa. And
thank you so much for having me.
Okay, then thank you everyone, and have a wonderful day, all of you. Thank you.